And then, okay, we'll dig into the subject of this course, which is the score generative model, score-based generative model. And I will give you, in fact, somehow a very simple introduction where there is no diffusion. You only need, in fact, to know what is the transition density and to somehow be familiar with Bayes formula. So that's for the first part. And okay, if time allows, I will give you another perspective on SGM, which is in fact a second approach which has been proposed by Paul and also in 2020. Okay, that's for today. And okay, there is enough material for 1 hour and a half. Okay. So just to give you, in fact, some kind of motivation, okay, for this course. So I just recall you what are energy-based model, right? So here, okay, I aim to design a generative model. So here, in fact, I need to specify a family of distribution parameterized by theta. And for energy-based model, okay, you specify this family of distribution by simply specifying a family of function, or energy function u of theta. And based on this energy function, you can define sequence of family of density, theta, parameterized again by theta. And this family of density are simply, in fact, density which are proportional to exponential minus u theta of x. And as we have seen in our last course, if you want, in fact, to apply the maximum likelihood principle, find the theta which fits the best your observation is I. There's a main issue dealing with energy-based model. Really that okay, you need to take care of these normalizing constants, which are in general tractable, and to do so, okay, you need somehow to combine stochastic gradient descent and MCMC algorithm. Okay. So that's okay, some kind of a reminder of the last part of the last session. And now, in fact, okay, I can, in fact, so I present you, in fact, another divergence, that's a Kullback-Leibler divergence, last time, okay, which is a score match, is the Fisher divergence. So here, in fact, I will recall you what is the Fisher divergence. So here, I suppose that's my data distribution mu star, I mean the density. Okay, so it should be mu star, so it was a typo. I suppose that my data distribution mu star is absolutely continuous with respect to the vague measure. And I did none by P star density. And I suppose that this density is smooth to begin with. And then, okay, if under this assumption, okay, and of course, if my family of density P theta is also positive and smooth, but it is the case in general energy-based model. All right, so here you can express the Fisher divergence between mu star and theta as simply the difference as the distance between the gradient with respect to x of log p theta and log of the gradient with respect to x of log of p star. And here, okay, you integrate with respect to the data distribution. So here, in fact, okay, my main motivation, yes, question.
If I understand well, if I remember well, P star is so empirical distribution.
Yes, exactly.
So this is not so smooth.
I will come to it later. Okay, give me just 5 minutes. So here I make a very huge assumption that everything is fine, and I am very tiny model where my data distribution is. But yes, I will come to it later. In maybe 3 minutes. All right. So here, in fact, so I present somehow my motivation for an energy-based model, but okay, in fact, this principle can be applied to any, in fact, problems that you can meet in statistics, where in fact you want to fit some parameter theta with respect to some observation for which in fact you have you suppose that it comes from an unknown distribution mu star. Okay. So that's now okay. So the first part, I will try to simplify if we could apply, in fact, if we could, in fact, minimize this divergence with respect to theta to find, okay, another parameter which fits my observation. Okay. So again, in fact, the main issue, as in the Kullback-Leibler divergence, if you remember well, is in fact, if you look at this function as a function of theta, you cannot in general evaluate it. First, even in fact, if B star is smooth, in fact, the first observation that you will need, in fact, the gradient of the log of the log density of your data distribution, and you do not have access to this distribution. But again, okay, you can simplify this function. So here you can write divergence between mu star and theta. Okay. You can write it as, then I just develop in fact the norm square there. I can just write it as the sum of the square of the gradient log theta of x d mu star, okay, square plus the integral of gradient log d star square d mu star. So minus the integral of gradients log d star of x gradient log theta x d mu star x. So here, in fact, I can see that okay, this function of theta can be decomposed into three terms. One of these terms, in fact, does not depend on theta. So in fact, minimizing this function of theta, in fact, I can disregard this term because it does not depend on theta. And now, okay, I just need the only issue which left to us is this scalar product with where you have still the gradient of the log density of the data distribution. In fact, to deal with this term, the only thing, in fact, you can use integration by parts. Okay, and by integration by parts, okay, if I denote A this term, okay, I can write A simply as minus the integral of the Laplacian of log theta of x in. Yeah, sorry, I forgot. Right. So that's tagged for this term. And now, okay, now you it's left so here you can show that in fact minimizing this divergence. Right. So here you have one answer. So here, if you now minimizing is that the divergence is equivalent, in fact, to minimizing the function with from theta, okay, gives you then the integral of gradient log theta x d mu star of x, then plus the integral of the Laplacian of the log theta d mu star. So now, okay, I can express in fact the minimization of this function of theta as in fact minimization of function of theta, which this time is integral with respect to the data distribution, but of functions which are tractable. Because I suppose that okay, I can have access to the gradients of the log of the likelihood, okay, and the Laplace. And now, of course, okay, again, okay, you do not have access to mu star, you have access to samples of mu star, and okay, the idea is as in the for the MLE, you just replace in fact the integral by Monte Carlo estimator, and that's it. And here it goes. Okay. So you obtain that somehow. I didn't lie to you, so yeah, it should be that to choose. But somehow, guess it's really equivalent to minimizing the empirical counterpart, okay, which is the sum. You sum over all of your observation inside, and you sum the norm of the gradient plus the Laplacian, and you want to minimize this function of t. So that's in fact the basic principle of score matching, and you can use it to train your energy-based model. And okay, that's been suggested by Evariet and its paper. And now, okay, one in fact, someone in the audience made the observation that okay, in fact, you do not know that the data distribution is smooth. And that's in fact the problem that we want to address in the following. Okay. And the idea, okay, it's pretty simple. Okay. So here, I will just consider smoothing approximation of my data distribution. So to do so, I will consider in fact phi of epsilon, which is the density of the zero-mean Gaussian with variance epsilon. Epsilon is a positive parameter, which is supposed to be small. Okay. And okay, I just compose. Okay, I in fact replace the data distribution by a smoothing approximation, which is a convolution of mu star and the Gaussian kernel. Nothing really difficult there. And okay, now by basic computation, I know that okay, mu star admits okay, if it admits some moments, okay, sufficiently large moments, I know that p star of x, p star of y, yeah. So sorry, mu star epsilon, I mean the density, okay, p star of epsilon of y, which is the integral of d mu star x phi of epsilon y minus x. And okay, with appropriate condition, moment condition on mu star, you know that p star of epsilon is smooth.
But this is still important now. This because now you don't have the density.
That's true, but still, in fact, here it does not really make sense to want to minimize this, okay, because the Fisher divergence is not even defined. So here, in fact, all the principle, in fact, it will make sense, okay, if you will know that, okay, it's that you would have, in fact, the data distribution is smooth. Otherwise, in fact, the Fisher divergence is infinite, so it does not really make sense. Okay, you could, of course, but
I mean, does it make sense that definition? But then with those computation you did, you get something that makes sense.
yes, I agree. But in fact, could you? But the main problem, okay. So could you still, in fact, check that it is divergence and that's really some kind of projection is not really clear. In fact, and it's I cannot really answer to your question, but it's yeah. And in fact, so from what And okay, another in fact, yeah, I will address your question now. Is that okay? One in fact computational facts. The here is that you need to compute the Laplacian. And as we'll see, in fact, if you regularize the bits of the distribution, in fact, the learning, in fact, applying, in fact, score matching to targets the smoothing approximation of the distribution, you will not need, in fact, to compute the Laplacian. So that's, in fact, some kind of, it's not the theoretical answer, but it's a practical answer. That's, in fact, one advantage, in fact, of smoothing also the density is that you do not need then to compute the Laplacian. Ah ouais. Then okay. So now I smooth a bit my data distribution. Okay, I consider now mu epsilon as mu star epsilon. And in this case, okay, that's in fact exactly what I just wrote here. Okay. Is that in fact the problem of minimizing then the Fisher divergence between mu epsilon star and mu theta. This time, in fact, even simpler than before. Why is that? Because here, in fact, you can show, yeah, I will, it's not really very difficult to show that, in fact, minimizing this quantity as a function of theta is equivalent to minimizing with respect to theta this function. And you can see this, that here, that everything, in fact, is again, in fact, the integral with respect to the data distribution of the tractable function. Here you have, in fact, the gradient x of log phi epsilon y minus x, which is completely, in fact, tractable. And this time, again, okay, you have the gradient of the log of theta of y, which is supposed also to be tractable. And here, okay, the main difference between with before, that this time, okay, you have, in fact, a double integral. Okay, so here, it's the integral with respect to mu star of x, and the Gaussian, in fact, phi of epsilon x minus y. So here, in fact, you can somehow, you can somehow, in fact, get rid of the Laplacian score matching by regularizing and paying somehow a double Monte Carlo approximation by something from the Gaussian. And that's why, in fact, you can, in fact, quite naturally replace, in fact, the fact that you can get rid of the Laplacian. All right. So here, in fact, for this, it's very easy. Like that, because in fact, the main observation to be made is that if I'm looking at, in fact, the gradients x of log of p of epsilon star y, okay. In fact, I can, using, in fact, the Fisher identity, I can still write it as, in fact, I can write it as a conditional expectation of this function. So here it's exactly. So here I can write gradients the log of the integral of p epsilon x y dy, where p of epsilon x y. Okay. So here, if you don't mind, okay, just to ease the presentation, but it's also hold for the general case. I suppose that okay, mu star and the density is flat. But okay, in fact, for the general principle would be the same. So here you have p of epsilon x of y this time is then just the distribution of the pair, in fact, x and y, okay, which corresponds to the convolution. So it corresponds, in fact, to p star of x by epsilon y minus x. Okay. And then in this case, you obtain just by the Fisher identity that it is, in fact, the integral of the gradients of the log of p epsilon y and x times p of y given x y. Oh. Sorry. So here now for this, in fact, since p of epsilon xy is equals to p of epsilon xy divided by p of epsilon y, just by Bayes formula, you obtain that, in fact, the equivalence. That's, and here, okay, I recognize exactly phi proportional up to constant in x times phi of epsilon x y minus x, okay, divided by, okay, let's show it. And so here you obtain that the gradient of log p epsilon x y p of y given x. So with, in fact, small computation, we can, if you remember, in fact, the expression of the Fisher divergence here. Okay. Now, what can be, in fact, shown from this small computation. So here, I recall you that, in fact, if I now do not consider mu star but regularization, I will obtain, in fact, the gradient of log of this star epsilon. Okay. And from, in fact, for my computation, just show that, in fact, the gradient of the log of I epsilon star y is, in fact, exactly the conditional expectation of the gradient x of log of p epsilon x y, p of y given x. Okay, and now, okay, just by using, in fact, the fact that the conditional expectation is a projection, okay, you can just, in fact, replace up to extend it your integral. You just need, in fact, to replace the gradient x log of star. Okay. You can replace it as exactly as I have here. Okay. I can replace, in fact, the gradient log of p epsilon x y. I can replace it by the gradient x log of phi epsilon y minus x. Okay. And here now I need to integrate not only on my my variable y, but I also need, in fact, to integrate with respect to the Gaussian variable associated with phi of epsilon. Yeah. But I will, okay, I will, in fact, also give you another perspective on this small computation in a few months. Okay, so that's, in fact, the what is called denoising score matching. And in fact, it's the basis of the training of score generative model, as we'll see. So here, in fact, I will use, in fact, this tool, and it's really at the core of score-based generative model.
Sorry, can you?
Yes.
Maybe I'm a bit lost, but it looks a bit strange that formula you are comparing p theta with psi epsilon. It's something doesn't depend on the problem.
No, theta depending on the parameter.
Yes,
So here, in fact,
but
you can see
your initial problem is that you are trying to get p theta close to one given p. And there you have a difference with psi, epsilon, and p theta.
Okay, maybe in fact I can give you another interpretation of this, which in fact that's why in fact it is called denoising. Yep.
It's a sort of deconvolution.
Exactly. So I will in fact give you more detail about it to give you in fact intuition about it. So here in fact if you look at now the empirical counterpart of this integral, what you would obtain. So here in fact an empirical Monte Carlo or empirical counterpart of this function, yeah, is simply okay. Here I just make a first change of form. I just make a change of variables first. Yeah, I can write it as d mu star of x, right? P of epsilon phi of z, the norm of z minus gradient x log theta. So here it should be x plus epsilon 1/2. Yeah. So here I can just make a small change of variable, okay, and just putting z equals in fact epsilon y minus x divided by epsilon 1/2. So here in fact you can see that the empirical counterpart of this is simply okay 1/n. The sum of the zi, and you can also already see it here, minus gradient x plus the theta of xi, that's epsilon 1/2 zi. And in fact, what you can observe here is that in fact what you would like for p theta, you can see it really as a denoising. Here, in fact, if I write it as epsilon theta I plus epsilon 1/2 I. So the I, of course, are the Gaussian random variables, standard Gaussian random variable. You can see it as, in fact, you want to find a function here, which from noisy observation try to predict the noise, and which is equivalent, okay, to just find a denoiser. That's why, in fact, it is called a denoising score matching. And really, in fact, that's how, in fact, you can find the theta, and it's a result by 3D. No, it's a result by Stein, which states to you that, in fact, it's an optimal. In fact, this is an optimal denoiser. Correct. Okay. Do you see? It makes more sense now. It's really that. So somehow that's why, in fact, in some paper, but in fact, it can be quite difficult at the first glance. You can see in some paper, okay, in fact, what people have said about diffusion-based generative model. They are, in fact, what you try to find. You try, in fact, to predict the noise, really based on, as we see, in fact, for a score-based generative model, that it consists, as I said, to, in fact, try to approximate a sequence of scores this time. And what you try to, what people say, okay, what you can read in some paper is that, okay, somehow score-based generative model try, in fact, to use somehow the main philosophy is to noise successively your observation and learn successively, in fact, different denoising at different noise schedules based on this principle. But I will be, in fact, I hope, clearer in a few slides. Okay, so now, in fact, I will apply this general principle to score-based generative models, and in fact, motivate this type of model by what I call discrete time reversal, and Giovanni will, in fact, make the hard part and discuss about the continuous time reversal. So a bit of history to begin with. So in fact, the first paper which introduced diffusion model are in fact quite an old paper, almost 10 years now. So you could not imagine, but yeah, so it was proposed by Schulz-Dickstein and co-author. But in fact, at that time, they didn't succeed in really, in fact, applying their model. It was not that impressive compared to GAN. But okay, all the idea was there. And in fact, what I will present today is in fact taken from this paper. And then, in fact, jointly, in fact, independently, Song and Hermont and co-author, in fact, revisit a bit the method by Schulz-Dickstein and co-author, but okay, make somehow some numerical trick, okay, and find out to make the model works. And now, okay, it's becoming very popular nowadays in machine learning. Okay, so here, what I will present you today is okay, very simple, I hope, introduction to score generative model by what's called the discrete time reversal. Okay, I will make, if I have time, link with Alain Durmus. It's called Alain Durmus. And if I have some time, okay, I will give you some implementation details and tricks. Cool. So in fact, as I said a few moments ago, the basic idea, okay, is as follows. So here, in fact, the idea is you sample from your data distribution, which is simply here a mixture of two Gaussian. And the idea, okay, is to successively noise your observation, meaning, okay, you in fact noise the data distribution up to, in fact, to obtain a Gaussian. And then, okay, from the principle I just show you about denoising score matching, the idea will be, in fact, trying to successively learn how to denoise, okay, how to predict the noise based on your noise data, and go backward, okay, go the other one, okay, based on this successive learning step, okay, meaning that now, if you have learned, in fact, the sequence of denoiser associated with sequence of noising distribution, the idea would be, in fact, to start from Gaussian, apply successively the denoisers that you have learned, and hope that it brings you to the generative, to the data distribution. Okay, so that's the big idea, the big picture. Okay, in words about score-based generative model. And now, okay, I will just for the notation, so I still denote new star the data distribution to ease the presentation, but again, do not polymerit this. I will assume that new star is the density P star. Okay, and here, okay, I will consider a base distribution, okay, a distribution which is easy to sample, from which, in fact, I will base my generative process, u0. And u0, okay, of course, will be, in fact, a Gaussian distribution at the end, with some variance, okay, and with 0. Okay, so let's let's see. So here the basic idea is as follows. So basic idea is to consider okay noising process of your observation or of your data distribution. And so here in fact it's naturally defined. Okay, the starting point is to naturally define a Markov chain. So here the idea is to define in fact the sequence xi from 0 to ns. Ns is my number of steps. And to will be in fact a non-homogeneous Markov chain, which will start from the data distribution, and you hope, okay. And if you know a bit about Markov chain, I think already you know it, but okay, you hope that okay, if you take a number of steps which is sufficiently large, okay, we could design a non-homogeneous Markov chain, which in fact from your data distribution will converge to the Gaussian distribution.
What do you say from mu0 to mu* in the first line?
No, it should be
The other way around.
no, it's the
Okay.
other way around. So, one of the typo of my slides. Thank you. Okay. So yeah, so here the idea is to construct a non-homogeneous Markov chain. I will give you in fact the expression of the non-homogeneous Markov chain in a few moments. But in fact, it's a kind of autoregressive model. And now, okay, based on the for this non-homogeneous Markov chain, in fact, it's equivalent to specify sequence of transition density, which I denote here by pk plus 1 given k. Okay, so here, in fact, pk plus 1 given k will be the sequence of transition distribution associated with this Markov chain, which in fact corresponds to the conditional distribution of xk plus 1 given q. Now, if I have the data distribution and its sequence of transition density, I in fact specify completely the distribution of my non-homogeneous Markov chain, and that's what I hope. Okay, that's for example, design this sequence of transition densities such a way that in fact x and s, okay, if ns is sufficiently large, x and s should have distribution close to mu0, which is again a Gaussian.
Non-homogeneous meaning time.
Yes. Okay. So that's why in fact I have in fact for any iteration I have one transition density, and that's no single transition density. Okay. And here the what follows, okay, denoted by x0, x and s, this Markov chain, I call it the noising process, just for the vocabulary. So here, okay, I just need some notation to proceed. So here now, okay, I can, based on what I already said before, now I can in fact exactly write the density of my noising process, of all my process, so 0 to x and s. It has quite a simple density. It's just a product of P0, where in fact, for simplicity, I denote P0 by P star. I denote P star by P0, sorry. Just to say that okay, it's my initial distribution. And now I just compose okay the pk plus 1 given k applied to xk plus 1 given xk. Okay. So it's just a basic definition of Markov chain, non-homogeneous Markov chain associated with a sequence of transition density. Now, based on this joint distribution, I can write completely like the marginal distribution of xk. Okay, the marginal distribution of xk is simply the integral of the joints with respect to all the other variables except xk, and that's it. And now, okay, in the next slide, okay, just to give you in fact a bit about the intuition about this model, I will suppose that x and s, okay, the distribution of x and s, okay, is p and s now, which has density p and s, is approximately a Gaussian distribution. And now, okay, what you would like, okay, is the question that you ask is that So here we go forward, okay? The idea is supposed to forward. You start from the data distribution and you go to the Gaussian, but in fact, for generative models, you want the other way around. Okay? You would like, in fact, to start from Gaussian and go to the data distribution. So in fact, the main idea is to reverse, in fact, the path. The main question now is that can we, in fact, sample a path, okay? X0, X, and S, not starting from X0, but starting from X and S, starting from a Gaussian. So that's, in fact, the equation. And so, the main idea is not writing, decomposing, in fact, the product of the joints forward in time, but simply, in fact, to consider the decomposition backward in time. So here, the main idea is just to write, in fact, P0 and S. Okay. Yeah, in fact, just by its formula, I can write it because everything is Markovian. I can write it as P and S and S. The product of K equals now NS to 1 of P K given K plus 1, K given X K plus 1. Where in fact P of K given K plus 1 is simply, in fact,
This is P_NS0 or P0.
sorry, NS minus 1.
No, but the one on the left, the first.
This one?
Yeah.
Yes. You go from 0 to N. The product of the
Is it possible to turn on some light there? Because
So is it fine or? But
I thought that one was from 0 to NS, and this was.
it's from 0 to NS, but you can show, in fact, that you can move. But you can show it, in fact, okay, it's not immediate, okay, if you want really to convince you, you can just use a very small induction. Okay. And where, in fact, pk given k plus 1 is k plus 1 is simply pk is a joint of k plus 1, of course, divided as k plus 1. So that's for based on this decomposition, I can consider, in fact, the backward decomposition. It's very small group, which I left to you. And now, okay, you somehow, in principle, if the world was easy, would in fact obtain directly a generative model, because okay, if I assume that PF NS, as I said, is approximately zero, mu zero, so Gaussian. And if you want, in fact, if you could, in fact, simulate exactly the conditional distribution of k given k plus 1, okay, you could have access, you could sample from data distribution simply by sampling from your Gaussian, okay, because here, in fact, XNS, sorry, should be, in fact, the initialization of your chain. And then, okay, you can go backward in time and simulate, okay, xk given xk plus 1. And for k equals 0, you will obtain a sample from your data distribution. But okay, here's the main issue, okay, but you cannot, in fact, have access simply to the conditional distribution of k given k plus 1, right? Because, in fact, here you do not even have, in fact, the normalizing constant, which is, in fact, the marginal, and as I said, in fact, the marginal distribution of the xk are huge integral. You integrate with respect to all the other variables. And even in fact, the marginal of the two variable xk and xk plus 1 is also a huge marginal. And so at the end, okay, you do not really have access to this two densities. But nevertheless, okay, as we'll see, the main idea is if we specify a bit now the non-homogeneous Markov chain, we will not, in fact, try to get an approximation of this ratio, which will give you, in fact, an approximation of this transition density. Because that's, in fact, the plan for the next slides. Okay. And we will obtain, okay, what's called, in fact, the discrete time reciprocal process, which, in fact, has continuous counterpart, which is this time exact.
But the transition probabilities of the inhomogeneous Markov chain, somehow they have to depend on the initial distribution, right?
No, you can, okay, but as we see, it's not mandatory. Yes. So I will give you, in fact, exactly the Markov chain I will use.
Because then from the Gaussian you go always go back to cats, I don't know. Even if you were trying to simulate the phase, I don't know.
No, because here, just give me the
Oh, sorry.
So the main, okay, maybe in fact what to answer to your question, in fact, what we'll do, in fact, somehow we still need, in fact, to learn, in fact, this transition density. And you will learn this transition density based on your observation.
Yeah, okay, yes.
But it will not depend on x0.
Okay, yeah, I mean,
you will learn,
yes,
in fact,
yes,
the
that's what I
transition.
meant.
Yeah.
Yes.
Okay. So now, okay, so what is the main question which I want to address? Okay, in summary, I want to address, okay, I will give you exactly the choice of the transition density that I will consider here. Okay, there are, in fact, several choices for transition density, but they are pretty much, in fact, on the form, they are very similar, but in fact, in practice, it may change, in fact, the results. And that's why, in fact, the people have considering different, let's say, noising process. And now, based on the choice of my choice, at least for the transition density, I will give you, in fact, some how to approximate this functional backwards density. So here are, in fact, here is rather the non-homogeneous Markov chain that I consider. Here, in fact, it's even homogeneous. So here, I will consider this Markov chain, which on the right. So I consider, in fact, an homogeneous Markov chain just like for simplicity, but in fact, you can make it non-homogeneous very easily. So here, I consider xk plus 1 equals alpha of xk plus square root of 1 minus alpha square dk plus 1. So it's a simple autoregressive process. And here, okay, you can see this as just some discretization, but exact discretization of an Einstein-Euler process, okay, at different time. And here, the Einstein-Euler process is simply this diffusion dxt equals minus xt t plus square root of 2 dbt, where bt is the Brownian motion. So here, okay, I will consider now not completely the autoregressive process. I will consider, in fact, the Euler-Maruyama discretization of this Einstein-Euler process. Xk plus 1 equals 1 minus gamma xk plus square root of 2 gamma zk plus 1. Where gamma, okay, is my step size, and zk is the sequence of Gaussian random variable. So now, and in fact, I will come back to it later, but if you want to define a non-homogeneous Markov chain, then you just take, in fact, the sequence of step size depending on the iteration. And in fact, the idea, as we'll see, that okay, you need in fact a time discretization which is smaller at the beginning because you want in fact to be very precise, clear the data, near the data distribution, but okay, at the end, in fact, you can take step size which is constant. So now, in fact, if I consider the Euler-Mariano discretization of the Gaussian process, it will not converge exactly to the Gaussian distribution, but very close. This gamma is small, okay, as you expect. In fact, you can show that the law of the xk converge to the Gaussian, the only Gaussian distribution with matrix, the identity matrix divided by 1 minus gamma watch. It's very simple, right? Because in fact, just write, in fact, xk plus 1 is 1 minus gamma. Yeah. That's well. Xk plus 1. And now if you just plug the expression for xk depending on xk minus 1, etc., and do an easy reduction, you obtain that it's equals the product of 1 minus gamma and here, which is k plus 1. Okay, it's 0, sorry. Plus square root of 2 gamma, the sum of 1 is gamma and minus k. K equals 0 to n minus 1 if no, sorry, it's 1 to n. If I remember correctly. So here what you can see that, okay, now at each iteration k, negligible, in fact, constant.
What is n?
Sorry?
What is
Sorry, it's k. Okay, mixed. So it's k, I, and that's k. So that's it. Okay. So now, okay, what you can see here. So you have an explicit expression, in fact, for the distribution of xk for any k. In fact, it's a Gaussian distribution with mean 1 minus gamma k plus 1 is 0. And with variance, okay, which is equals to 2 gamma this square. So here, in fact, the variance is 2 gamma, the sum of 1 minus gamma and minus 5.
That K, that I, that I.
Yes. Then you can see that in fact the mean with k, as k goes to infinity, the mean converges to 0. Whereas in fact the variance, you can compute exactly the variance there. And you can see that in fact, if and here, so here we have the 2, that's fine. And that's it. So I'm almost done. So here we have 2 gamma as k goes to infinity, 1 minus 1 gamma square. And here, okay, the 1 will simplify in the denominator, and you obtain 2 gamma per 2 gamma minus gamma square. And if you simplify by 2 gamma, you obtain exactly 1 divided by 1 minus gamma over 2. Oh. So pretty much, okay, yeah, I have defined my analytic process. So here, in fact, it's a homogeneous Markov chain, but you can imagine just taking a sequence of step size which depend on the iteration. In fact, you can pretty much the same. You can show that converge close to the Gaussian is by sequence of step size is 0 or is small. and you obtain a time homogeneous Markov chain, which now makes the job. So now I take, okay, as my nosing process. Now, based on this nosing process, can I, in fact, can somehow make a guess, sorry, about some kind of an approximation of the transition density of xk given xk. So let's try if we can simplify a bit based on some intuition. So it's not completely, it will not be completely mathematically rigorous, but you could make it, in fact, let's say rigorous if you have time, then, but it's a bit technical. Yeah, I consider pk given xk plus 1, xk given xk plus 1. So here I will start from the formula I gave you before. It's just the ratio of the jump divided by the marginal. And here, okay, I can write it, in fact, also based on the base formula. I can also write it as p k given k plus 1, xk plus 1 given xk, k plus 1 p k xk divided by pk plus 1 k plus 1. So here is just the base formula. Okay. If you have done a bit of Bayesian inference, you can, in fact, it brings bells to you. So now, okay, let's try to play a bit with this expression. Why, in fact, I'm quite happy with this expression, because here this time, at least I know one there. Yeah. The term which I know is the condition, so it's k plus 1. Of course, I didn't drink enough coffee this morning, so it's okay. So it's pk plus 1 given. So now, in fact, why now I'm quite happy, because I know at least one term, which is this one, which I just specified in the last slide. And now the idea is to write it as an exponential. So here I can write it, I plug exactly up to some constant which does not depend on xk plus 1. So here, in fact, remember that I just want the density with respect to xk. And I do not bother with constant and also function of xk plus 1. And so here it's proportional as a function of xk, as pk, as exponential minus xk. So plus 1 minus 1 gamma xk, square divided by 4 gamma. It didn't finish. And here, in fact, I just plug the pk plus 1 and pk in the exponential, and then, okay, I can write it as a difference of log, and also the other points which I make a change. I can always, in fact, multiply and divide by pk xk plus 1. And so as a function, in fact, of xk is still proportional to this exponential plus then the log of pk k minus the log of pk plus 1 xk plus 1. So idea is just that, okay, someone wants to compare the same function, but does not really change, because here, in fact, I would like just to identify the conditional density and conditional density with respect to xk. So I can, in fact, have to changing normalizing constant, I can just change, in fact, p of k plus 1 xk plus 1 by pk of xk plus 1. Okay, so now let's try to simplify a bit this expression. So first, okay, the main intuition I will make based, in fact, on my definition right here. By definition, in fact, what's intuitively I can assume that, in fact, the difference between xk plus 1 and xk is of order gamma. Just because, okay, if I just make the difference between xk plus 1 minus xk, I obtain gamma xk plus square root of 2 gamma zk plus 1. Okay. And here, so it should be more something like square root of gamma. So now, based on this idea, what in fact can show here is that I can in fact simplify a bit this norm square, because now what I would like more that in fact the mean should be a function of xk plus 1 and not a function of xk. So now in fact I would like to in fact switch the role of xk plus 1 of xk. And to do so, what you can show is that xk plus 1 minus 1 minus gamma xk square is pretty much, in fact, xk minus 1 plus gamma k plus 1 square plus the big O gamma. That's not difficult, right? And here, so it's even gamma. Okay. So that's, in fact, if you develop, in fact, this norm square, you develop also this one, not really complicated based on this approximation. So you can see that, in fact, a first order approximation of this norm square, in fact, where you try to switch the role of xk and xk plus 1, gives you that, okay, for this term at least, it should be a mean. The distribution of xk should be, in fact, a Gaussian distribution within 1 plus gamma xk plus 1, just for this term. We didn't finish yet, because in fact, we need also to handle the second term here, which of course change also the Gaussian distribution.
The correction is for the gamma, because it was square root of gamma square, or
No, it's gamma square. It's gamma square.
okay.
Sorry.
Okay.
So now let's try to deal with this second term. So here for this second term, okay, I do not have many ideas, okay, but if you do analysis, okay, the first idea you have is just to do Taylor expansion. Okay. And so if I do, in fact, Taylor expansion, more, in fact, about pk plus 1 with respect to a log of pk okay, I obtain pretty much that's in fact the log of pk xk. Okay. Gradients of the log of pk pk okay. Okay. And here it should be pk. sorry. So it's pk xk plus 1. And here it's xk minus xk plus 1. So here I have the scalar product between the gradient of pk xk plus 1 applied with xk minus xk plus 1. And plus a PO of gamma, because I know that the second term, okay, it would be in fact a big O of xk plus 1 minus xk to the square. Okay, and so here I have the square of gamma, and I obtain in fact as a first approximation gamma. That's in fact the leader term on the difference between log of pk xk and log of pk xk plus 1 is in fact this scalar product here. And now, in fact, if I combine these two results, I can simplify, in fact, this exponential. And in fact, we can simplify it here. So now, in fact, I obtain the P k given scale plus 1. Okay. It's proportional to exponential norm square of xk minus 1 plus gamma k plus 1 square divided by 4 gamma. The scalar product between the gradients and the difference of xk minus xk plus 1. Right. Okay. This one. Xk minus xk plus 1. And plus a big O of gamma. So now up to, in fact, an approximation of the exponential of size gamma, and you can remember that gamma should be in fact somehow a small parameter in principle. This, in fact, you can recognize that it's a Gaussian distribution, okay, as in fact, if the variable is xk, and you can just complete the square, and you obtain that in fact it's this conditional distribution of xk given xk plus 1 corresponds to in fact exactly some Gaussian distribution which mean 1 plus gamma xk plus 1 plus then 2 gradient log pk k plus 1 and variance. Yes. So it's an approximation, of course, okay, in gamma. But still, okay, so can use in fact this proxy try to approximate in fact the backward transition kernel between xk and xk plus 1. And now why in fact you are quite satisfied? Because here in fact this transition density this time are completely tractable, except in fact the mean. Okay? But the mean this time is the score at iteration k. And if you remember well, okay, the score pk is just in fact a noising of the theta distribution. And in fact, learning the score of pk is exactly the same as denoising score matching. It's exactly what we've seen in fact at the beginning of the night. So that's like in principle. So here. Okay, still 15 minutes, that's fine. So here, okay, I gave you in fact the backward. Yeah. And now, okay, what you would have access, in fact, to exactly to this core. The first approximation, of course, is to start from a Gaussian, okay, with this covariance matrix and follow the successive approximation of the transition density which you just found, okay, which just corresponds to simulate between xk, yk plus 1, which given yk is equal to yk plus gamma yk plus 2 gamma gradient log of pk yk plus square root of 2 gamma ck plus 1. Now, okay, the main issue, okay, as in fact is square matching or denoising square matching, is to learn exactly the score of the noising process at iteration k for any k. Okay. And to do so, okay, we can use the principle which I give you exactly at this when we start the course. And here, the idea is really as in denoising score matching. So here the idea is just simply to write gradients. That's in fact somehow some computation I did for GMS. So here I can compute the gradient of log pk. Okay. This time, okay, is exactly it's maybe it's okay. So it's gradient log of the integral of p0, so 0, k equaling 0, k given it's 0. Because remember that, okay, I know exactly my term of Genus Markov chain. It's very simple. And given x0 from the previous formula I just write you on the board, I know exactly the distribution of xk given x0. Okay, so some Gaussian distribution which mean, okay, 1 minus gamma, so for k times x0 plus some Gaussian noise, okay, with the variance that you can completely explicitly compute. So now, okay, if you just apply as again the Fisher identity, you obtain that in fact it's integral, okay, of the gradient of the log p. Now, so here you need scale. Okay. So here it's the gradient of the log of p. Okay. Now, check that. Okay. So 0 by 6 0 xk. Xk given x0. And now k x0. Right, now it's was the way just wants to do the computation, so it's okay. Five. And that's fine. And now type this. That should be x is 0. Oh. So what you can see this as in fact in the first part of the course, and I want to be more precise and do it more slowly. So you can see that in fact the gradient of pk at xk is exactly in fact the conditional expectation is in fact, if I'm right, it's in fact with the end, it corresponds to the conditional expectation of the gradient of the log of xk, given x is 0, given that xk equals small xk. And here, in fact, you integrate with respect to x. So now, based on this observation, you can really see that trying to minimize, try to approximate to the score, okay, just by characterization of the conditional expectation as a projection, you would like, in fact, you want to try to estimate the projection of this fact of the random variable gradient of x log of p of xk given x is 0. Okay. And that's also, in fact, another approximation. In fact, another. So here you want to approximate the gradient. This random variable is gradient log of pk xk. Okay, well, this time is a random variable. So if you want, in fact, to approximate this random variables, you can just, in fact, plug it into a regression problem. Okay. And use, in fact, that the conditional expectation is exactly a projection in L2, meaning that, in fact, the gradient of pk taken from this expression corresponds to the hard mean of this function over all the function f, which belongs to the L2. And again, in fact, this minimizing this function. Okay, so here, in fact, you can see that the expectation is not only on x as 0. The expectation this time is, in fact, with respect to xk and x as 0, as in fact with denoting score matching. And in fact, you can have, in fact, you can have, in fact, a Monte Carlo estimate for this functional for any f. And then, if now f is parameterized by theta, we can have an empirical counterpart of this quantity and try to minimizing using stochastic gradient descent. Okay, so that's in fact what I just wrote for. And just to maybe make a completion. So now, in fact, if you have a family of function parameterized by theta, so typically, in fact, sorry, a neural network. So here now, okay, the way to there is now of theta. But you can try, in fact, you can try to approximate the gradient of log of pk. Then by minimizing then which from theta gives the expectation of the null as theta. Okay. Minus the gradient log of theta given 0. Okay. So 0. And here, okay, as I said, the expectation is with respect to xk and x0. And in fact, empirical counterpart of this function It's simply okay based on n facts observation is 1 over n. For I equals 1 to n of the norm of f that is ki minus the gradient line then given 0 the I is 0 I square. So x0 I would correspond in fact to earlier observation. And xki is just in fact some noise, some noisy in fact observation. So xk0, xki, so xki, so xk. It's just in fact individual Markov chain and dependent Markov chain such as g plus 1 I is equals to 1 minus g I plus over 2 g plus I 1 I with starting from the 0 I. That's the dependent.
So that what you put in a rectangle is really a definition.
Yes, it's exact. It's an exact expression.
No, but it's a definition. It's not a gradient. It's a mean gradient. It's the expectation. Because it's not evaluated in a point. X.
Yes, it should be. Yeah, yes, I forget. My previous expression was correct. That's positive. Yeah.
There is X.
Yeah.
So there is XK. Why you are sampling to understand? If you are sampling XK, means that you're making an average over XK as well.
Yeah. So here, in fact, you approximate in average the gradients. So it's a regression problem. In the regression, you never, in fact, approximate exactly the function. You approximate it in average. When you have the features in your prediction y, in regression problem, typically you have x and y, okay, the features and the label. And here, okay, when you try to find your regression solution, in this case, you will in fact try to find a function which in average, in fact, corresponds to your prediction. Yeah, thank you. Oh. So that's in fact okay. So and here okay, everything is explicit, okay, because you know that you know in fact explicitly the Poynesian distribution of xk given x0, okay, it's again just a Gaussian distribution, and here it is explicit, and so here you can implement it exactly this function and use okay your favorite optimization algorithm to try and to optimize over the parameter theta. Just also a small point, okay, here what can be in fact quite if you could get rid of in fact and minimize another function, okay, just by using an integration by parts, and you would obtain in fact another function here if you also this case to approximate, which in fact is which corresponds to the second expression I'll give you for the score matching, but I will not into the details. The last comment which I would like to make is that here, in fact, you can see that at each iteration k, I play with, in fact, a family of function of theta. So in practice, okay, you will never use, in fact, NS neural network to approximate all the score. You in fact consider one neural network which will be parameterized, in fact, which will take as inputs, of course, your current points, xk, but also in fact the time, okay, which corresponds this time to gamma k. And then, okay, so you in the end you do not consider ns neural network, you just take one neural network which takes in input the state xk, but also the iteration where you are, or in fact if you believe in the continuous time, plus the continuous time counterpart, which is time gamma k. And now the idea is just to combine, okay, all this loss, okay, for any iteration. So here you sum over the observation, but also you sum over all the iterate of your Markov chain to obtain, in fact, the final loss of your neural network parameterized by the time and the states. And you sum over all the iterates of your noising process, and you weight a bit, in fact, each individual loss associated at each iteration to learn the current iteration k. And here what, in fact, and but I will stop there, but what is quite important is the choice of the weights here. In fact, there is plenty of paper which try to find insight about how to optimize from in an optimal way, in fact, which weight you should put there. But also, and I didn't really discuss it because I use, in fact, an homogeneous Markov chain, but as I said, you could, in fact, make, in fact, different discretization steps for the Neurostein process, which correspond, in fact, to not taking just gamma, but a sequence of steps as gamma k. In fact, the choice, but the story would be the same. You would not have just k gamma here, but in fact, the sum of gamma I for I equals 0 to k. But the loss is exactly the same in the story as well. But now, in fact, there is a lot of paper. In fact, the training of score generative model is very sensible to the choice of the weights and the step size. And in fact, there are plenty of paper about it, but short story short. In fact, you need to be very precise, in fact, at the beginning, of course, because in fact, it comes from the fact that the score at the beginning is brilliant smooth. And learning a score which is not very smooth is, of course, more difficult than learning a smooth score. And also, the lambda k should be, in fact, proportional to 1 divided by the variance of your noise. Okay, because here, typically, in fact, empirically and intuitively, you can see that, in fact, the typical, in fact, range of this function, okay, behaves in 1 over k gamma. So here, in fact, you should take, in fact, lambda k as of order k gamma. So in fact, I give more detail in the slide if you're interested, and make some link about, as in fact in the paper by Song and Herman with Annie Langevin, the Annie Langevin algorithm, and make in fact details about the other approach with the ON co-author. But okay, I think time goes by and I need to leave you here. But if you have any questions, do not hesitate to contact me. Thank you very much.